Hello class. This video talks about the capacity index Cp. Before starting this video, you should first read the slides to get an idea of the definition for the sigma 0 and how to obtain the value for sigma 0. So this Cp is a capacity index and is defined as the tolerance divided by the capacity, the process capacity. We have discussed three cases comparing the tolerance and the process capability in our last class. Now we can relate this Cp value directly to these three cases. So in case 1, the tolerance is greater than the process capability. So everything we produced is within the lower specification limit and the upper specification limit. So this is a desirable case. And in this case, the Cp value is greater than 1 because your tolerance, the differences between the USL and LSL, is greater than your process capability, the 6 sigma. In the second case, the tolerance and the process capability are equal, therefore the Cp value is 1. As you can see, you have the same value for the numerator and the denominator. In case 3, the tolerance is smaller than the process capability. That means even though your process is in control, there are still tails of your process that are not conforming. So you're still producing non-conforming products even though your process is in control. So this is an undesirable case. And in this case, the Cp value is less than 1 because your tolerance is smaller than the process capability. We still use the same keyway example as we used in chapter 5 throughout this chapter. So in January, we have this process capability with the sigma 0 equals to 0.038. And then we keep improving this process. So in July, this process capability has improved, so the sigma 0 is decreased to 0.030. And now assume that the specifications are 6.50 and 6.30, so this is the upper specification limit and the lower specification limit. And then I want you to determine the capacity index, the Cp value, before and after the improvement. So before the improvement, this sigma 0 is 0.038, right? And then your enumerator is the differences between your specifications. So that's the 6.50 minus 6.30, and then divided by the 6 times the sigma 0 value. So this gives a Cp value of 0.88, which is smaller than 1, so it corresponds to the case 3, which is undesirable, right? And then after the improvement, this sigma 0 is decreased to 0.030. The USL and LSL are still the same, so our enumerator is still the same, but our denominator decreases, so the Cp value increases. And after the improvement, this Cp value equals to 1.11, so it's greater than 1, and it is actually in case 1. So we improved our process capability from the case 3 to case 1, from an undesirable case to a desirable case. So from our example and from the analysis according to 3 cases, we can tell that the larger the Cp value, the better the quality. So how can we get this larger Cp value? When the design engineer is going to set up the specifications, he or she should consider the process capability and therefore to set up a realistic specifications. On the other side, we should continuously improve the process capability. So when we reduce the variation, when we reduce that sigma 0, then we can get a larger Cp value. In industry, the minimum capability index is frequently established at 1.33, and this is considered by most organizations to be a de facto standard, so it's like an in effect standard. Below this value, design engineers may be required to seek approval from the manufacturing before the product can be released to production. So that means if the value is below 1.33, that means you have very small flexibility of any variations from your process to conform to the specifications. And if we want to have a higher CP value, if we want to set the CP value to 2, then it requires that the specifications to be set at plus and minus 6 sigma.